In this video, we're going to be finding the integral from 1 to 8 of arcsecant of cube root x dx. So if we look at our bounds, 1 and 8, these are actually cube rootable numbers because 1 cubed is 1 and 2 cubed is 8. And we also have a cube root of x right here. This suggests that we have to use a substitution of u equals cube root of x. So let's do that. Let u equal cube root of x. And to get our du, we're actually going to cube both sides to make things easier and remove the radical. So cubing u gets us u cubed, and cubing the cube root of x is just x. Taking the derivative of both sides, we just get 3u squared du is equal to dx. Let's plug it into our new integral. So we have integral, and we have to change our endpoints. So 1 actually becomes cube root of 1, which is 1 again. And 8 becomes cube root of 8, which is 2. We have arcsecant of cube root of x, which is u. Dx is 3u squared du. I'm going to move the 3 outside of the integral and then the u squared to the front of the arcsecant. All right. Now notice that we can easily differentiate arcsecant of u and integrate u squared. This suggests that we have to use integration by parts. So let's do that. We have integral u dv equals uv minus integral v du. So let's choose our u and dv. We can make u equal to the differentiable one, so arcsecant of u, and dv equal to the u squared. Taking the derivative of arcsecant of u and u to get du is equal to 1 over the absolute value of u times the square root of u squared minus 1. And integrating dv to get v, we get v is equal to u cubed over 3. All right. Now, what? All right. So now what we're going to do is we're going to multiply the u and d. We're going to multiply the u and v together and then minus the integral of v times du. So multiplying u and v together, we get arcsecant of u times u cubed over 3 and minus the integral of v times du. So u cubed divided by, and then this denominator times this denominator is going to be 3 times the absolute value of u times the square root of u squared minus 1. All right. Now, all this right here is just equal to the integral of u squared arcsecant of u du. But we want 3 times this integral, not just this integral, but we want 3 times it. So let's multiply both sides by 3, and multiplying something divided by 3 is just going to cancel. So I'm just going to write a slash there, and then multiplying by 3 here, we have a 3 in the denominator, so that's also going to cancel. So now we have arcsecant of u times u cubed minus the integral of u cubed over absolute value of u times square root u squared minus 1 du. And We also have to include our bounds of 1 and 2, so let's do that. We have to evaluate this term from 1 and 2 and put bounds on this integral. Let's put on here as well. All right. Now, let's evaluate this first u cubed arcsecant of u. So first evaluate u cubed arcsecant of u at 2. That's going to be 2 cubed times arcsecant of 2, which is just 8 cubed, which is just 8 arcsecant of u. 8 arcsecant of. First, we're going to evaluate u cubed times arcsecant of u at 2. So that's just going to be 2 cubed times arcsecant of 2, which is just 8 times arcsecant of 2. Equals 8 times arcsecant of 2. And we're going to subtract. Now evaluate this at 1. So 1 cubed times arcsecant of 1 is just arcsecant of 1. All right. Now our main focus is this integral. Now we want to get rid of this absolute value of u because you don't know how to integrate this. But we can actually look at our bounds. We have the bounds of u equals 1 and u equals 2. And notice how absolute value of u is equal to u only when u is greater than or equal to 0, right? Because only if u is negative, the absolute value bars will change like the value inside, right? The absolute values only work, like they only function if the value inside is negative. But if it's greater than 0, greater than or equal to 0, but if it's greater than or equal to 0, if it's positive or 0, then it doesn't really do anything. And if we look here, we have u values of 1 and 2. So we can actually treat absolute value of u as just u. So I'm going to rewrite this integral as negative integral from 1 to 2 of u cubed divided by, and instead of absolute value of u, I'm simply going to write u times the square root of u squared minus 1. Now I can happily cancel out the u cubed and u just to get u squared on the numerator. So now I have the negative integral from 1 to 2 of u squared divided by u square root u squared minus 1 du, right? Now I can evaluate this with a trigonometric substitution. So because I have a squared, because I have a u squared minus x, because I have a u squared minus a squared, I'm going to let u equal a times secant of theta. But a in this case is just 1, so 1 times secant theta is just secant theta. That way du is equal to secant theta tangent theta d theta. Now we have to change our endpoints, so let's do that. The lower bound is going to be turned into u equal to 1, so I'm going to plug that into this. 1 is equal to secant theta, arc secant of 1 equals theta. So our lower bound is turned into arc secant of 1. And now our upper bound is just going to be 2 equals secant theta, so arc secant of 2 is equal to theta. Arc secant of 2. And to rewrite the numerator, we just have u squared, and we know that u is equal to secant theta. So u squared is going to be secant squared theta divided by square root u squared, again, is secant squared theta minus 1. And du is secant theta tangent theta d theta. All right. All we have to do now is solve this integral. So now we have minus integral from arc secant of 1 to arc secant of 2 of secant squared theta divided by, and recall that from our Pythagorean identity, secant squared theta minus 1 is equal to tangent squared theta. Now, if we take the square root of both sides, we just get square root secant squared theta minus 1 is equal to tangent theta. And that's basically what we have on the denominator. We have square root secant squared theta minus 1, exactly that. So let's replace it with tangent theta in the denominator. So we have tangent theta in the denominator times secant theta tangent theta d theta. All right. Now we can obviously cancel the tangent theta here and the tangent theta here to get our integral as negative integral from arc secant of 1 to arc secant of 2 times the tangents are gone, so we just have secant squared theta times secant theta. Notice how I did not combine them to make secant cubed theta. I did this because we can actually integrate secant squared theta quite easily, and we can differentiate secant theta quite easily. This suggests another integration by parts. So we have integral u dv equals uv minus integral v du. Let's choose our u and dv. We have u to be the differentiable part, so secant theta, and the dv equal to the integratable part, so that's secant squared theta. Differentiating u, you get du is equal to secant theta tangent theta d theta, and integrating dv, we get v is equal to tangent theta. All right, so now we have that the integral of secant squared theta times secant theta d theta is equal to uv, so secant theta times tangent theta minus the integral of v times du. This is just going to be secant theta tangent theta times tangent theta, which is just secant theta tangent squared theta d theta. And if we recall from the same trigonometric identity I showed you here, tangent squared theta is equal to secant squared theta minus 1. I'm going to substitute that into here. So now I have negative integral of secant theta times secant squared theta minus 1 d theta. Distributing the secant theta to both terms in those parentheses, I have negative integral of secant cubed theta minus secant theta d theta. Now I'm going to split this into two integrals, and I'll show you why. Minus integral secant cubed theta d theta minus becomes plus integral secant cubed secant theta d theta. All right. Now I'm going to bring this secant theta tangent theta down here, secant theta tangent theta, and now I'm going to rewrite this integral, secant squared theta times secant theta, as simply secant cubed theta d theta. Now I can actually add the integral of secant cubed theta d theta to both sides, and I simply get 2 times the integral of secant cubed theta d theta is equal to secant theta tangent theta minus and plus becomes 0, just cancels, plus the integral of secant theta d theta, which we know is natural log of absolute value of secant theta plus tangent theta plus c. Now to isolate for our final integral that we wanted in the beginning, which is integral of secant cubed theta d theta, I divide by 2 both sides. So now I get that the integral of secant cubed theta d theta is equal to 1/2 of secant theta tangent theta plus 1/2 times the natural log of the absolute value of secant theta plus tangent theta plus c. All right, so we solved the integral of secant cubed theta, but what do we actually want? We wanted the negative integral of secant cubed theta, d theta, from arcsecant of 1 to arcsecant of 2. So let's find that. We wanted the negative integral, so let's apply a negative to both sides. So now we get negative 1/2 secant theta tangent theta plus minus 1/2 natural log of absolute value of secant theta plus tangent theta. All right? This negative integral is equal to this. However, I don't think that's all we actually need, because we're evaluating this from arcsecant of 1 to arcsecant of 2, but I think there was more that we needed. We had this, 8 times arcsecant of 2 minus arcsecant of 1. So let's include that. So we have 8 times arcsecant of 2 minus arcsecant of 1. And we have to evaluate this whole thing at arcsecant of 1 and arcsecant of 2. All right? So let's evaluate this at arcsecant of 2. So we have negative 1/2 secant of arcsecant of 2. Obviously, you can cancel that, but I'm just rewriting that. Times tangent of arcsecant of 2 minus 1/2. I'm just plugging arcsecant of 2 in for theta. So negative 1/2 ln absolute value of secant of arcsecant of 2 plus tangent of arcsecant of 2. Right? So I plugged arcsecant of 2 in. Now I'm going to subtract the value when arcsecant of 1 is plugged into here for theta. So I'm subtracting this. So I'm going to, in my head, I'm going to apply a negative to this whole thing. So this negative term is going to become a positive, and this negative term is going to become a positive. So instead of writing negative 1/2, I'm going to write positive 1/2 secant of arcsecant of 1 positive 1/2 natural, and this is multiplied by positive 1/2 of secant of arcsecant of 2 of 1 times tangent of arcsecant of 1. Right? And I'm going to write, again, positive 1/2 natural log of the absolute value of secant of arcsecant of 2 plus tangent of arcsecant of 2. All right? Now, this is actually going to be our final answer for the integral. I know this was a lot, but this is our answer. Oh, what? Why did I write arcsecant of 2? What? ln. Okay, please tell me this is it. Yes! All right, so we have this 8 times arcsecant of 2 minus arcsecant of 1. Now we have to evaluate this whole thing at arcsecant of 2 and arcsecant of 1. So let's plug in arcsecant of 2 in for data. So you have minus 1/2 times secant of arcsecant of 2 times tangent of arcsecant of 2. By the way, I know I can cancel this out, but I'm just not going to because I'm just going to write this on my final answer. So we have that minus 1/2 natural log of the absolute value of secant of arcsecant of 2 plus tangent of arcsecant of 2, right? Now we have to evaluate this at arcsecant of 1. We have to subtract it. So subtracting this whole thing is just going to be minus minus, going to be plus 1/2, and this is going to be plus 1/2 as well. So I'm going to do plus 1/2 of secant times arcsecant of 1 times tangent of arcsecant of 1, right? Minus turns into a plus because minus a negative becomes a plus. So plus 1/2 natural log of the absolute value of secant of arcsecant of 2 plus tangent of arcsecant of 2. And absolute value. And that's actually going to be our final answer. All right. This is a pretty long one. There's probably another way to do this, much more easier, but this is how I found it to do it. This is how I did it. And if you want to know like the decimal answer, this is around 5.987. All right, this is going to be the answer for this integral.